think we can start with our keynote now. This keynote is different from a typical HPC. We never had something about quantum when it comes to keynote. But this time, using quantum as accelerators and an HPC machine, that was attractive for us. And I'm happy to see that this approach, we are just getting quantum inside the HPC machine using, standard schedulers. That's why we went with this and made it like a keynote. So Roberto and Gabriella, they are going to give us this introduction. Let's see how that will go. Yeah, thank you. Please join me to welcome them.
Hello everyone, I'm Gabriella Bettonte, and today I'm here with my colleague Roberto Rocco. Together we work in the HPC and quantum computing group at T4 Computer Engineering. Well, the title of our talk is How Not to Decelerate Your HPC Workload with Quantum Computing. We know that usually HPC talks focus on acceleration, but we also know that HPC experts often fears that introducing quantum computing in their workloads can actually slow them down. So we want to reassure you with this talk, it is possible to introduce quantum computing into your workloads and still harness the potential of these new emerging technologies. Before I start, I would like to spend a couple of words about who is E4. E4 is an Italian company based in the Data Valley near Bologna, and for more than 20 years we have been delivering HPC hardware and software solutions to enterprises and research centers such as Sineca, CERN, Leonardo. Lately, E4 has been also involved in national and European research projects about quantum computing. Let's start by talking about heterogeneous computing. Heterogeneous computing refers to the usage of multiple types of processors within a single system. Of course, the most known example is coupling GPU with GPUs, but lately more other components have been added to the picture, such as, for instance, FPGA or quantum processing unit, and possibly more. In this scenario here, each processing unit type is optimized for specific tasks, and this allows workload to be assigned to the most suitable processor. This heterogeneous approach enhances both performance and energy efficiency. Before expanding on heterogeneous computing, let's spend a couple of words about quantum computing and what makes quantum computing that powerful. As you can see from my slide, starting from 1994, which is the year Shor algorithm has been published, the academic interest toward quantum computing and the number of publications on the matter has been increasing. Not only that, across the world, we have the growing public and private fundings keep financing research about quantum computing. The global effort for 2025 has been estimated around $45 billion. Also, the industry around quantum computing is becoming increasingly vibrant with rapid growth across startups and also larger enterprises. But why quantum computing is that interesting? Well, for specific problems, classic computing is expected to deliver a solution in an unreasonable amount of time, while quantum computing is promising to reduce this to a reasonable, meaning polynomial amount of time. For now, the quantum algorithms that are offering such a gain are quite rare. One famous example is the Shor algorithm that we mentioned also before, and this algorithm is meant to factor a number in its prime numbers. This is quite interesting because the factoring is an operation which many cryptographic protocols rely on. Even before fulfilling the theoretical promise, quantum computing is promising us can bring other benefits, such as producing more accurate results or doing that with a smaller energy footprint. Before proceeding, we need to understand why quantum computing is that hard to understand. Well, it is because it's completely different from classical computing. Quantum computers are not meant to be the next generation of supercomputers. They are relying on a totally different physics. That's why now I'm giving you a couple of concepts of physics that are useful to keep understanding the rest of presentation. In classical computing, we have that the basic unit of information is the bit, and the bit can be 0 or 1. Well, in quantum computing, the basic unit of information is a qubit, and also the qubit can be in the status 0 and 1, but we can have also another state, the superposition, that is representing all the possible states between 0 and 1. When we measure a qubit, it will collapse in either the 0 status or 1. We can think about the superposition as the probability of the qubit to be measured in either 0 or 1. We can create qubits by manipulating different quantum systems. For instance, we can build a qubit using a photon or an electron or an atom and other physics components. And according to the choice we do, we can have different quantum machines. Finally, I need another concept here, quantum entanglement. Quantum entanglement is a physical phenomenon that occurs when a group of particles interacts. It is impossible to describe each particle quantum state independently from the other, even if the distance between those particles is quite significant. When two qubits are entangled, they both exist in a superposition. When I measure one of those, both will collapse, and the status of one qubit will have opposite position with respect to the other one. Well, the three concepts that we saw, qubits, superposition, and entanglement, are the key ideas on which quantum computing is relying. We can store more information using those specific characteristics of quantum computing. And that's why quantum computing is promising to be that powerful. We have many different quantum computers. It depends on the choice we do to build a specific qubit, but we have also other different features. We have two main categories, analog quantum computer and digital quantum computers. The analog ones are also called special purpose computer because they are meant to solve only one kind of problem. Usually they are employed to solve optimization problems or quantum physics simulation. They are quite promising because they can go now up to 1,000 qubits. And then we have the category of the gate-based computers. Those are called universal computers because they are supposed to solve any kind of problem. Here we have prototypes with much lesser qubits compared to the analog one. We say that we are now in the NISQ area. That means noisy intermediate scale quantum, because we have computers that have only a few qubits, and they are quite sensible to noise. And in the future, we hope to have fault-tolerant quantum computers. We have in the slide also another category that is called classical computer, because they rely on classical hardware, usually GPUs. And here we have the so-called quantum emulators. Quantum emulators are, again, classical computer that allows us to emulate the behavior of a quantum computer. They are useful to start developing algorithms and also for debugging and test the results of an actual quantum computer. Even if emulators are powerful and super useful nowadays, they have limits. As an example, we can see here an experiment that was made by Jülich last year. They used Jupyter, an exascale machine, to emulate 50 qubits. And just to emulate a small amount of qubits, they require a lot of memory. And for each qubit then you add, you need to double the memory. So it becomes unfeasible quite quickly. Okay, so we talk about the physics, the underlying physics behind quantum computers, and we spoke about those emulators that are allowing us to start building algorithms. But the question is now, for what can we actually write those quantum algorithms? We have, in mathematics, we have a different class of complexity in which problems are categorized. We have the polynomial problems, and those are the problems that I can solve in polynomial time. Those are easy to deal with. Classical computing is totally fine with them. And then we have the non-deterministic polynomial time class. Here we have problems that might not be solved in polynomial time, but I can verify the solution in polynomial time. And we have that many real-world problems are in this category here. When quantum computers start to appear, the mathematical researchers question themselves about which kind of problems can actually benefit from quantum computing. So another category was created, the category of bounded error quantum polynomial problems. Here we have the problems that I can solve with a quantum algorithm in a polynomial time with a small chance of errors. And it's not clear now which kind of problem can fall into this category. We have some example. We have the sure example we mentioned before to factor a number. We have also the Grover algorithm to find an element in an ordered vector of elements. So examples are there, but there is not the vision of all the problems that can be mapped into this category. Still, we can rely on those examples to start exploring more quantum algorithms, but how can we use the quantum computer? Well, we need at first to initialize the machine to the initial quantum state, and we do that by employing a superposition mechanism, for instance. Then we evolve the initial state using some unitary gates in case of gate-based computer, and then I measure the result. If you think about what we said at the beginning, let's imagine to have a qubit in a superposition of 0 and 1. When we measure that superposition, the qubit will collapse in either one state or the other one. So this is a probabilistic operation, and being a probabilistic process, we need to run the quantum algorithm multiple times to extract a probabilistic distribution that is meaningful. And here we are talking about thousands of shots. So thousands of repetitions of the experiment. Well, ideally, when we finish to run our algorithm, we will have that the most counted solution is also the good one. But doesn't happen all the time because of quantum errors. Here we have a problem for the HPC integration. The fact that we need to repeat so many times the quantum algorithms to have a reliable solution is one of the pain point in integrating those devices as accelerators for HPC. Well, we mentioned quantum state. Quantum states are quantum states are affected by quantum decoherence. This means that over time, the quantum states of the system can lose the information that was brought by the entanglement and the superposition. And in a quantum circuit, we see that this will produce quantum errors, meaning that the quantum computation is not fully reliable. But that's fine. It's also it's a probabilistic process, and also in classical computing we have errors. But in classical computing we can copy bits, and rely on redundancy to correct those errors. We cannot do that in quantum computing because of the no-cloning theorem. Then we have a new field of study that is building quantum error correction techniques. We had also a talk yesterday about this topic. It's a real hot topic, and we can also think about here the usage of HPC to help with those techniques. Those techniques are quite expensive. We need to correct errors. We need an overhead of physical qubits that are representing logical free qubits. Well, I've been talking about a lot of issues about quantum computing, but if we look at where we started, the present is not at all so dark. We started in the 90s with experiments that were done in university lab, and researchers were able to just trap those ions and not perform operation on those. And nowadays, we have many different kind of commercial prototypes relying on different physical protocols. They can go even up to 1,000 of qubits. So it's quite a promising, an impressive advance of the hardware. Also, the software is not waiting for the hardware to catch up. There are many research initiatives to ensure that the software is efficient, maintainable, reusable, and cost-effective. This means that we are trying to have quantum software respecting the same standard that classical software is doing. And then, even if there is not a clear understanding of all the problems that can benefit from quantum computers, there are efforts towards many fields of science, for instance, chemistry or scientific computing in general, cryptography, that we also mentioned before when speaking of Shor algorithms. So eventually, we'll come up with a bunch of algorithms that will benefit from those devices. And again, we have already example of those. But I started my talk speaking about heterogeneous system and modular architecture. We are starting to think about modularity also in the quantum module. Until now, quantum vendors are trying to squeeze the biggest amount of qubits into a device. That is still working, there is still space for that, but at some point we will reach a limit. So researchers are starting to think about putting many quantum computers together, and the focus now is shifting to link those quantum processors. The idea is that having a smaller computer will be easier to maintain and also manufacture them. There are many challenges linked to this idea. For instance, it's not clear how to maintain the entanglement, meaning the information across the QPUs. Then it is not clear how to physically link those QPUs. And then also we need to develop efficient compilers to deploy the separation of quantum circuits across the QPU. Then I will leave the floor to my colleague that will explore more how those quantum devices can be integrated into modular system. So please, Roberto.
So thank you, Gabriella. So right now up to now we talked about quantum computers as a standalone. So why integrating them with HPC machines? Well, they kind of solve compatible problems. Let's put it this way. So while we are talking about HPC, we are trying to get the maximum performance out of our machines. And quantum computers can can provide a result even faster for some problems, not all problems. They're not universal computer, as Gabriella already told us. And while achieving a fast response, they also consume less power. And I have a slide later that shows you this very clearly. So why not join forces? Why not having HPC for all the part that quantum computer cannot withstand, and accelerate then the algorithms compatible with quantum computing through offloading to a quantum computer? So this can work because it takes the benefits of both worlds, but it has also some criticalities because the two worlds are very, very spread apart. They're very different in terms of a lot of aspects that we're going to see. So the integration is promising, but it's not trivial. I have right now a slide to visualize better the power consumption of the machines. Those two are two pictures I took at the PSNC, the Poznan Supercomputing Centers. On the left, we have two racks with HPC machines inside. And on the right, basically, I think there are two racks of quantum computers. Those should be trapped ions, right? Yeah. And I want to point you the difference between the number of cables that go in from the roof to the machine. That's a visualization of power consumption, basically, because I cannot consume power if I cannot transfer power to the machine. And as you see on the HPC side, we have plenty of very thick cables, while on the right we have just a very slim one. So that's the comparison between the magnitude of power consumption of the two machines. That's why we are trying to do this integration, because quantum machines also promise a very good energy efficiency, which is a topic more and more important for HPC users. So, which applications can benefit from this integration? Because not all quantum algorithms are suited for a joint integration with HPC, because sometimes we don't need HPC resources for that. But for some applications like condensed matter physics, quantum chemistry, and combinatorial optimizations, we see that there are benefits in having some part of the code running on HPC and some algorithms running on quantum computers. So those are the three use cases leading the integration between these two worlds. Of course, they may not be the only ones. Those are the most promising, but we may still discover new fields in the future. So I think this is enough to delve into it. And how do we do this integration? Well, as we stated that quantum computers are not standalone, I mean, they can be used standalone, but are not general computers, and they fix only some algorithms, it becomes quite clear to have them like GPUs, like accelerators for some particular kind of problems. And so we have this, this schema in which the quantum computer is an accelerator. It just works on small data, solving very complex problem with the small data, and transfer then the result to the HPC, who does all the pre-processing, post-processing, and well, they together solve the problem entirely. This approach actually is what has been pursued a lot in Europe, because right now in Europe we're starting to have quantum computers. We have them installed in France, Germany, Czech Republic, and Poland, and Italy and Spain and Netherlands are having, and also Luxembourg are having their quantum computer installed. The nice thing about quantum computers in Italy, in Europe in general, is that they have different technologies. We're not just focusing on superconducting quantum computers or ion-trapped quantum computers, because we still do not see the clear path or what is the technology that will be the best. And also, different problems may favor different technologies. So right now we are just having like the complete spectrum at Europe level, and so that each researcher can choose the best machine for its own problem. Okay, so what's the current status of HPC and quantum computer? Because we need to make this integration, but let's see what we're talking about. On one side we have HPC, which has been there since many, many years, so we have established technologies, and we rely on parallelism to get to the performance. We have heterogeneous hardware because it integrates different technologies, but overall they're quite the same in terms of programming structure. And we have many nodes, a lot of available resources we can use for our parallelization. On the other side, we have quantum computers, which are not so mature. I mean, they have not been around for many years, so developing code for a quantum computer is tricky because it's not mature, there's not maturity in the software. Performance comes out not from parallelization, but from the properties, the quantum properties of the machine. And we have this diversity of technologies, a lot of different approaches for the same problem. So integrating all of them is tough. But what I want to focus on this talk is the last aspect. We have that, well, the one to last aspect. Quantum machines right now are a very scarce resource. They're very rare. We don't have many in our environment. If we have one attached to our HPC cluster, we are already lucky. So how can we ensure that everybody gets access to those without having some issues? Well, if we want to do an integration, for sure we want it to preserve the HPC stack as much as possible, because that's consolidated. That's something that is validated. It's used by the people in the HPC. But we still need to bridge this gap, so we will have to bring the technology of quantum towards HPC. But here comes the issue. We have two directions we can follow for this integration. On one side, we have pure HPC solution. Well, quantum is a resource. We provide a quantum partition. You get your quantum resource reserving through Slurm. All that. OK, fine. So I request for my HPC quantum execution some HPC resources, some quantum resources. But quantum resources are very scarce. So I wait a lot of time just for that quantum part. On the other side, we have how right now quantum is mostly used. So it's somewhere in the cloud. You can offload it through accessing through REST APIs, etc. Very high level. And it works, but we lose the benefits of having a tight integration, because now we really don't know where the machine is. So we want a tight integration because quantum is producing a lot of data, and with just a cloud solution is not enough. So what are the challenges overall of this integration? We have different languages, but this comes from the different level of maturity, as we stated, because quantum is way newer than HPC in this sense. Different availability. We have very few quantum machines compared to HPC nodes, and this leads to two different research directions with what concerns integrations. On one side, we have the actual integration, so how do we put those machines together, what are the protocols, what are the algorithms, etc. And on one side, and that's the one I'm going to present today, is once we have this integration, how do we handle the different resources present in the system? And the nice thing about this second research direction is that it's possible to address it from the HPC point of view. It's quite similar to just an HPC problem. And that's why we're here talking in an HPC AI conference, despite it's a quantum presentation. So here is the resource contention challenge. We have few quantum machines. If I reserve a quantum machine and I'm not using a quantum machine, there's a queue of people waiting for me. So if I just reserve it at the beginning, and then I do some mixed computation, sometimes I do some HPC, then I switch to quantum, then I switch to HPC, well, the quantum machine is never full. But that's our bottleneck, because we just have a few of those machines. So we need a way to provide a resource allocation a little bit smarter. It should be more dynamical, because otherwise we just have a lot of people waiting for resources and nobody gets them. So we are worsening the overall utilization of the cluster. Also imagine that if we just add a quantum machine, you reserve your classical resources, wait for the quantum resources, but in this case, you're also worsening the utilization of the classical resources, because a lot of people are just reserving resources and waiting. So in the end, just attaching the machine worsens your performance. Here, and hence, how not to decelerate, the title of the keynote. So through our research, we tried to address this problem through the Smart HPC QC project. It's an Italian project in collaboration with Sineca, BSC, Università di Torino, Politecnico di Torino, and Links Foundation. And the idea is to provide some solutions to this resource allocation problem. And I said solutions, plural, because there is not a single solution. You see, quantum machines are too diverse. They have so many different technologies, and each technology has a different time span. From superconducting quantum machines that are very, very fast, they can perform shots very fast, to not neutral atoms, which may take minutes to hours to perform a complete quantum execution. So having a single solution that fits both scenarios, I mean, it may work, but it doesn't fit all. So it's better to have multiple solutions. And those solutions should basically go over the static allocation of resources. And so the first two solutions we envisioned were taken actually from the HPC field. And those are workflow. So basically, we are taking the execution of the HPC QC workload, splitting into parts, and queue them through resource allocation separately. And this simplifies the thing because the quantum job, we never request for both classical and quantum resources. We just split it up. Thus, the queue for the quantum job is separated from the queue of the HPC jobs, and everything can work anyway. On the other side, we have the malleability. Sorry for the Y on the other line. The malleability solution, which is basically, okay, all this problem comes from the fact that we are requesting all the resources at the beginning, and we cannot change them. But what if we can change them? What if we can request and release resources as we execute? This is something that has been explored in HPC for a very long while. We have many tools trying to do this. Still, we have some problems in their interaction with the resource manager, but we can see this. Okay, so we have two possible solutions. Let's try to, well, play with them on a real example. Actually, more of a toy example, because remember, quantum computers still have some limitations, so we need some example. If we just take a real-world example, it may be difficult, also because they're difficult to access. And for this part here, we are okay just to simulate them. But more on this later. So this is the flow of our application we're testing. Basically, it's a clustering application. We have multiple points, we want to classify them, and we have some parts executing on HPC and some parts that executing on quantum. In particular, we have multiple clustering algorithms. We simulate them in HPC, we collect all the results, and then we basically select a clustering which comes from the union of the clusterings found by the various algorithms. And so basically, the solution should not have overlapping clusterings and should minimize the distance, etc. So here is, we do this through a quantum computer. And then we evaluate the score. If the score is fine, okay, we finish. If it's not, we iterate again. So as you see, we're doing some workload on HPC, some workload on quantum, and iterating, alternating. Okay, so we simulate this on a very simple sandbox cluster that we use to evaluate whether resource contention can provide some issues. We have worker nodes. Actually, it's not one, it's more than one. We have 3 of them, but that's enough also. And a quantum emulator, which is a little bit more powerful. It also has a GPU for quantum emulation, a network switch, some other nodes for Slurm setup, etc. And the idea is, let's see how all these resources, all the application behaves over those resources in this scenario. So we executed it first and foremost, just took the application and made it execute, integrating it with the workflow and malleability solutions. And we saw that if we execute a single application, we do not lose wall time. And that's good, because we are introducing some functionalities, and once we execute a single application, there is no resource contention, so we do not expect some benefit. But actually, we get no malus for this, so this is good. So what if we introduce resource contention in the form of we had a second workload asking for the same resources? Well, in that case, one might take the resources while the other will wait. I mean, take a look at the graph on the left. Here we just show the HPC resources. The first line is the baseline, so we just request all the resources for one job, the blue one, then all the resources for the orange job, so the orange is waiting. But it's waiting also when we just need the quantum resources. And that's why the workflow behaves better, because we release the HPC resources while we need the quantum resources, so that the other job can interleave its execution. So overall, we reduce our compute time. And the malleability works in a similar way. We are reducing the amount of resources when not needed, so that basically the two jobs can work together, adjusting the resources. So overall, we execute the two workloads, the sum of the two workloads, faster, and we use less resources overall. Okay. These experiments were done on a sandbox cluster, very small one. But we also validated them on Leonardo, the Cineca supercomputer. So we're trying to expose our execution to real workloads, to real resource contention present in the cluster. And we showed that basically malleability and workflow solution both provide great benefits compared to a statical allocation. While all these experiments still are pure HPC experiments. We didn't use quantum computer up to now. We just emulated the behavior of quantum machine. So, but those are not the only experiments we did, because we also carried out a third solution, which is virtualized QPUs. You see, if the execution is very, very small, the execution of shots is very compact, having to release and request again those resources adds a lot of overhead to the execution. So it may not be the best solution. The best solution would be to share the quantum resource. And we do this by virtualizing it. As you see on the bottom, we have two GRS with the quantum computer. And they basically do time multiplexing, so that once we execute one, once we execute the other. And so we're basically raising the utilization of the quantum computer without affecting too much the two applications. And we tested these both on our testing environment with HPC nodes, but also through the help of the quantum computer installed at Linux Foundations. So here we have a different application. It's no longer a cluster algorithm, because that benefited more from workload and malleability. We have a graph coloring problem application. And basically, each node wants to execute some part of it on a quantum computer. And we do this through our vQPUs. And as you see, we are evaluating the results based on occupancy of the quantum machine and on total time, so the time to complete all the workloads. And as we see, if we raise the number of slots in a quantum computer, so we raise the possibility to allocate it concurrently, we get lower quantum occupancy for each copy. This means that we have more of the QPU we can use for later workloads. So we're we unlocked more the potential of the QPUs. And overall, the total time, having more copies, lowers because we can do more quantum computation in parallel. So this is our three solutions: malleability, workloads, and virtualized quantum processing units. And here is our take-home message. So HPC is already heterogeneous, so why not include quantum computing in this as an accelerator, not as a replacement? And they provide benefits for specific problems. They're not universal machine, they're just very specialized. And we must address the presence of quantum machine in our clusters, because up to now, they're a scarce resource, and if we just integrate them seamlessly, we are worsening the performance of both the classical and the quantum jobs. So there are plenty of challenges in this, and if you have any questions, here are some references, and we're here for you. Thank you.
Thank you. Any questions?
Thank you for the talk. Have you found any useful applications using quantum and classical together?
Well, our simple toy example is just an experiment to show the potential benefits. Right now, we're working on the quantum chemistry, right? We want to say something.
Maybe I can elaborate on that. Yeah, that was just a toy application to experiment, but we are working on application in the field of quantum chemistry that is believed to be the most promising one. But to be honest with you, in quantum computing conferences, this question is raised very often, and there are few examples so far of application that can have the both valued. Let's see what will happen. There is a lot of interest toward that question.
Any other questions?
Thank you for the nice talk. I was wondering, when you showed workload and malleability, like it seems the results were super positive because like average wall time and utilization was better, but from the that was for 2 workloads, and assuming now you have like multiple workloads coming from multiple users, if you focus on the perspective of the single user, would it be the case that the performance of the workload is way less predictable compared to the case where like it's exclusively allocated?
Well, on one side you may say it's less predictable. On one side, on the other, I can say, yeah, it's more predictable once you get the resources. But if I have a queue that is variable, I can start from the beginning or I can start at the end. So it's the variability changes. Basically, working with malleability forces us to think, to shift the focus rather than on a single user on the whole machine and trying to maximize the utilization. So maybe we're not executing the single jobs to the fastest, but we're trying to use the machine as much as possible, and so having the entire machine more energy efficient. Because if everybody just focuses on its own job, yeah, it goes slower indeed, because we're releasing resources that we could use to go a little bit faster. But maybe those resources could be more useful to someone else, and overall the whole competition of everybody, the sum, the average, is lower. So yeah, we can have lesser guarantees that we're going fast, but overall we're consuming way less energy. And this focus is quite important with the shift towards energy efficiency.
Maybe if I can add, from the HPC supercomputing perspective, it's not good to have the scarce resource not used at the maximum level, and there are mechanisms for users to ask for exclusive usage if they need to. There is already this mechanism for classical resources, so why not for quantum if reasonable.
Yeah.
Thank you.
Any other questions? Okay. Oh. No.
Thanks for the talk. I have a question regarding the multiplexing that you do, because many of these machines have got very long tuning times before they can actually compute. So having to switch between more than one workload could incur in a very high price in terms of preparation of the registers and whatnot. For instance, the Pascal machine has a very considerable tuning time before you can actually start performing the computation. So if you are swapping between two different workloads, you're wasting a ton of time every time.
Yeah, that's true. That's actually a problem, a significant problem, and that's why we propose multiple solutions. The Pascal machine is a neutral atom solution which takes a lot of time to provide an answer. So a virtual QPU solution for that machine is not feasible because we just spend way too much time switching between one and another. That fits more superconducting solutions because the execution time is shorter. On such machines, maybe the two approaches of malleability and workflows should provide better results, in theory.
Yeah, I can elaborate a bit. Yeah, that's what Roberto said is totally true, according to our experiments. Again, we didn't have the opportunity of using the real neutral atom machine, but that machine will be installed in Cineca, so it's one of our future plans to validate on the real case. And then I do agree that building the register in the neutral atom machine is quite a long process, but we can think of some application which we reuse that register many times. But again, yeah, I understand. So let's see what happens with the real machine.
Yeah.
Future plan, anyway.
Yeah, in those cases, we may also have some policies in the resource scheduler to avoid too much job swapping, or at least have some similar jobs, like with similar quantum parts that we don't change too much the initialization. We can have something like that, but that's all the reasoning within the scheduler.
Well, it may happen that the dynamic approach doesn't fit one specific kind of quantum machine. If that is the case, we can go back to the static approach. We are exploring, as we said, we do have so many machines, and those approaches can be beneficial for some cases. And we saw with the Lagrange machine that they have at links. The virtual QPU approach was promising, so it was a nice result. We'll see at Cineca they will have two different kind of machine. At the supercomputing center they have also the trapped ions we saw at Potsdam. We are exploring those solutions. Yeah.
Thank you very much for the talk.
Thank you.